We are going to look at amide hydrolysis in acid solution to a carboxylic acid. This is exactly the same chemistry that we saw when you took a nitrile to a carboxylic acid. This is just the second half of that mechanism, because you initially did have to make an amide in that particular reaction. So if you can do that one, you should be able to do this one. Okay, so here's an amide, and you're going to do this in acid solution, so there's some form of acid. It's usually an oxyacid in water. Now you are going to use this proton from the acid to protonate an electronegative atom, and you have two choices, the carbonyl oxygen or the nitrogen. If you give it to the nitrogen, which is a possibility, you have no resonance delocalization of the positive charge. But if you give it to the oxygen, you will have 3 resonance structures. And if you have resonance, you're always more stable than without resonance. So give it to the carbonyl oxygen so that you can have resonance. So oxygen's going to come in here, pick up the proton, and we'll give electrons back to the oxygen. Alright, so there are resonance structures for this species. Oxygen can take those electrons in the double bond and take them to itself, making the carbonyl carbon positive. If that is positive, the nitrogen can also act as an electron pair donor to that carbon. So you've got a total again of 3 resonance structures as you do this. I'm going to redraw that first one there on the left, but be aware that there is a good amount of electron delocalization of the positive charge, which makes this a very favorable place to do the protonation. Okay, here's the resonance structure we were looking at. Now, after the proton has been given up, you also have water in the solution. Water is not usually a fantastic nucleophile, but you've now protonated your initial amide, so it now is susceptible to nucleophilic attack, and water will add as a nucleophile toward the carbonyl carbon, and you will break the pi bond. And you can do this from any one of the resonance structures you want. By doing so, you will make a new tetrahedral intermediate, which is protonated. What we're going to do now is proton transfer through solvent. So your solvent again is water. And it will come in and accept the proton, and you'll give electrons back to the oxygen. And this is how you make the neutral tetrahedral intermediate. Now what you're going to do is a proton transfer from solvent to the tetrahedral intermediate. And you could give this proton to either of those two OH oxygens or to the nitrogen. Any one of them can accept it, but to do something productive, give it to the nitrogen. So we're going to show nitrogen acting as the electron pair donor to pick up the proton and give electrons back to the oxygen here. What we've done by doing so is created a very good leaving group. So now what you can do is use either one of those OH oxygens and use their lone pair electrons to make a pi bond between the carbon and the oxygen. As that occurs, something has to go, so you kick out ammonia. Now this intermediate that we've just created again is a protonated form of a carboxylic acid, and it does have resonance structures. Let me draw them very quickly for you. So we have resonance stabilization of that positive charge again. At this point, the ammonia is going to remove the proton from the oxygen, and it doesn't matter which of these two oxygens gives up its proton. I'm just going to show it from this one, and then you give electrons back to the oxygen, creating at the end your carboxylic acid. And ammonium.